Okay, so one thing is, so if at all, if that RAR file, if it is not supported by your system, that WinRAR, if you have not installed, you cannot install it. So that could be the one problem. Okay, so you can just check that one by installing WinRAR in your systems. So other than that, I think you can check that. So other than that, I'm coming to the Mac thing. So in the last class itself, we have told that so that doesn't support for Mac OS, and as we said, so we don't know. So whatever we have that exists only for these things. So you can check in the internet if you want. Okay, so as far as the information what we got from the lab instructors, so there is only a paid version for it. That also we are not sure which one and all to share with you guys. So and I don't think that I don't suggest you to buy that what those things and all. Okay. Yes sir. Background noise. So now
okay. Too much noise from background.
So my voice is audible now, right? So that background noise will end, sir. No need to worry about the background noise. Okay.
ಚೆನ್ನಾಗಿ ಪಾಠ ಕೇಳ್ತಾನೆ ಕೇಳೋಣ ಒಂದು ಕ್ವೆಶ್ಚನ್ ಕೇಳಿ ನೋಡೋಣ.
ಅಭಿಷೇಕ್,
ತುಷಾರ್, ಶೈಲಜಮ್ಮ, ಜಾನವಿ ಜಾನವಿ ಮೈಂಡಲ್ ರೆಕಾರ್ಡ್ ಐತೆ ನೆಕ್ಸ್ಟ್
ನಾನು ಡಿಸ್ಟರ್ಬ್ ಮಾಡಿದ್ರೆ ನನ್ನ ಕ್ಲಾಸಿಗೆ ಡಿಸ್ಟರ್ಬ್ ಮಾಡ್ತಿದ್ದಾರೆ. ಸೈಲೆನ್ಸ್ ಅಂತ ಹೇಳಂಗಾದ್ರೆ ಹುಡುಗರು ಕಾಲ. Okay guys. So regarding that Mac thing and all, so if at all, if you can somehow get some Windows PC, you can. Not audible? Okay. So if at all, if you can somehow get the Windows, you can try in that one. Okay. So else you can execute it once you are back to college. Okay. So this is all about the regarding the lab. So I think I can move with the actual syllabus now. So let me start recording the session. Minutes. Record on now. Good morning guys and welcome to the ADE session. And in the previous class we were done with the fixed bias circuit, collector to base bias circuit, and we started with the prevalence. In the prevalence we have seen the approximate method. So these are the topics we discussed in the last class, correct? So any doubts in those sessions? So if people are having any doubts, you can interrupt me. So else we'll start with today's session. So as I told you in the last class, this voltage divider bias can be analyzed by using two types. The first one is by using approximate method and the second one is by using accurate method. In the approximate method, again some more. Okay. Okay. So in the approximate method, what we are going to do, we are going to, so guys, so guys, I don't know, some construction work is going on here, some repair work. So because of which this noise is coming from the background. Okay. Okay. So here in the approximate method, what we are going to do? So we are going to approximate the values, right? So like how we assume I2 is approximately equal to I1. Okay, so we assume that the base current is zero. This was the approximation what we did, and we calculated the value of IC as well as VC. So now we are moving on to the accurate method. So on screen you are seeing the circuit diagram for accurate method. So here what do you have? It is a voltage divider bias circuit. Okay, so here you have your transistor. Okay, so this is the transistor, NPN transistor. So here, this is the collector terminal, this is the base terminal, and this is the emitter terminal, as you can see. Okay, so RC resistor that is connected to the collector terminal is called as RC resistor. Resistor which is connected to the emitter terminal is called as RE resistor. Current flowing through this resistor collector terminal is called as IC current. Current flowing through emitter terminal is called as IE current. Okay. So similarly, when you come to the base side, since we are using a voltage divider network, the applied voltage is VCC, which is divided by using this two resistors R1 and R2. Okay. So R1 resistor, R2 resistor. Okay, so or you can also call it as RB1 since it is connected with this base resistor. Okay, so this is R2 resistor, and current flowing through R1 is called as I1, and current flowing through R2 is called as I2. The current flowing through base resistor is IB resistor. So this is the IB, a very simple circuit, very simple
If it is not visible,
divider circuit. Screen share madam.
Every screen ಮಾಡಲಿಲ್ಲ.
Your entire screen. I'll ಕೆಳಗಡೆ ಕೆಸರು share. So now we go back to the page. It is visible. Okay. So this is the circuit for the voltage divider bias circuit. So don't worry about this DC equivalent. So that is not there. So actually this is why this is called as DC equivalent circuit. So this is not a complete circuit. So this voltage divider, so guys, this is not there for your syllabus. I'm just telling you this DC equivalent. Okay, so no need to worry. So still it contains input capacitor, output capacitor, all those things. And it also contains AC sources. So now we have removed all those things and we have considered only the DC equivalent circuit of it. Okay, so that's why this name is there. So you can simply write voltage divider bias circuit. So this diagram is from the voltage book. That's why you have that name. Okay, so don't worry too much about those things. Yeah. So now, so I hope that you people have studied about this Thevenin's theorem. Correct. So answer is or no. So you have already studied this one.
ಇದು ಲೋಡ್ ಆಗ್ಬೇಕಾ?
So you have already seen this Thevenin's theorem, right? Yes. Have you heard of this? Yes or not?
ಎಷ್ಟು ನೀಟಾಗಿ ಒಂದು ಮಿನಿಟ್ ಬೇಕಾಯ್ತು.
So A section, guys, is the screen visible now? Okay, the screen sharing is happening. Okay. We got to know that it's not visible. Okay. Okay, guys, stop. So we are sharing it. Okay, section people, yeah, we are sharing it. It will be done. Okay. So now answer me. Have you heard of this Thevenin's theorem? How many of you know? Okay.
No.
No, fine. Stop sharing. Maybe up here immediately. Yes, sir.
ಇಲ್ಲಿ ಸ್ಟಾಪ್ ಆಗಲ್ಲ ಮನ್ಸಾಗುತ್ತೈತೆ ನಮ್ಗೆ ಸ್ಟಾಪ್ ಆಗುತ್ತಿಲ್ಲ.
Full screen. You share your entire screen. I'll read scale this out. Sure. ಆಗಲಿಲ್ಲ. ಹಾಂ ಇವಾಗ ಹೋಗು ಸ್ಕ್ರೀನ್ ಶೇರ್. ಈಗ ಇನ್ನೊಂದ್ಸತಿ ಮಾಡು. ಇದು ಇಲ್ಲಾಂದ್ರೆ ಅದು ಇದಾಗಲಿಲ್ಲ. So A section students now. Now can you see? Okay. Cut okay guys, so it will be done. So meanwhile we'll just see this one. So what is this Thevenin's theorem? So here the circuit contains too many voltage sources and too many resistors, so then it's difficult to apply KVL if you have more than one loop or so many loops. The loops are overlapping, so then you can't simplify it by using simple KVL. Okay, so in such cases we are going to make use of this Thevenin's theorem. So what this will do? So this will a complex circuit. Okay, so what it does, it combines all the voltage. So all the voltage source, since more than one voltage exists here in the circuit, so all those sources will be replaced by a single Thevenin's voltage. Okay, so all those many voltage sources can be simplified by considering only one Thevenin's voltage. Okay, so similarly all the resistors can be clubbed and it can be replaced by using a single resistance, RD. Okay, so Thevenin's resistance. So now the circuit, so now whatever you are seeing on screen is a simplified. Yeah, this is for A section people. Okay, so because the screen was not visible, I'm just repeating it. Okay. So here on screen you can see this is the voltage divider bias circuit. Okay, so this is the transistor, this is the base terminal, this is a collector terminal, and this is the emitter terminal. Okay, so this is RC, this is RE resistor. So here this is the applied voltage VCC, and here there is a formation of the voltage divider. Okay, so you can see here the voltage, applied voltage VCC is getting divided by using these two resistors R1 and R2. Okay, so this we have already seen even in the approximate method also. So now I was talking about the Thevenin's. So since this circuit is a bit complex to solve just by using the KVL, so because of which we are moving or we are taking the help of the Thevenin's. You can just compare these two, those two circuits. So here all that resistance at the input side, whatever we had the voltage divider circuits, resistors we have removed, and we have simplified it by using simply the one resistor RT. What is that value? We will calculate it. Okay, so next similarly we have simplified it to an equivalent VT. So then what is this RT and VT? See, this RT is a Thevenin's equivalent resistor. What is the value of this RT? Since this RT is determined by R1 parallel to R2, and that's what you had in the circuit, right? So you had R1 which is parallel to R2. So here R1 is parallel to R2, which you have reduced this one to R2. Then you can tell this RT is equivalent to the all the input side resistance. So when you take a R1 parallel to R2, okay. So here when I'm just substituting the value. So because to include all these things in a KVL, I may land in a confusion. I may okay. But here one simple loop is there. So in which I can apply KVL easily. But what is RT? RT, I cannot assume the value of RT, right? So RT was formed by the clubbing these two, and these two existed in parallel. So to take up the value, I have to calculate the R1 parallel R2. Okay, so what is the formula? So this formula you know how to calculate the resistance in parallel, R1 into R2 divided by R1 plus R2. Correct. So this is how we are doing it to calculate. This is what we are doing it to calculate the Thevenin's resistance. And coming to the voltage and this by voltage division rule, so people have studied this. Okay, so what is VT is equivalent to Thevenin's voltage is equivalent to the voltage divided, the voltage in the voltage divided by a circuit. So what is it? So it is nothing but the applied voltage VCC into other resistance. Okay, R2 resistance in the other branch R2 divided by the sum of those two resistance R1 plus R2. Okay, so this is equal to VCC into R2 divided by R2. Okay, so now that we have simplified, it's very easy for us to apply the K. Okay, so since the circuit is simple, so this is almost equal to our collector bias circuit, correct? So now it looks like that, similar to that. Okay, it's not exactly, but similar to that. So since we have only two loops, input side one loop I have and output side one loop I have, I can easily apply the KVL. Okay, so let's apply KVL to the base emitter loop. Okay, so what is this base emitter loop consists of? So this portion. So you start from this VT. Okay, so it is starting from this VT and it includes this ITRB, RTIB and this VBE, it includes, okay, so and it ends in this IR, very simple, right? So this loop, okay, so this loop I'm talking about, so input side loop. Okay, so let's apply KVL. So how to apply KVL here? So I'm starting from this VT minus plus VT, taking it in the negative side. So if we, LHS side, if you write everything in the LHS side,
the numbers are
minus you have to write. But we have written it in the RHS. VT is equal to VT minus IBRT minus VBE minus IBR is equal to 0. Okay, so this is the KVL VT minus IBRT minus VBE minus IBR. Okay, so next we know what is the formula for IE. IE is equal to 1 plus beta into IB. Okay, so now in place of this IE, I am substituting this 1 plus beta. Okay, so this by transistor theory we know this. Okay, so if I substitute in place of IB 1 plus beta IB, so I can just rearrange the terms. So what is my interest? So I want to calculate IB. Why do you want to calculate IB? Just to calculate IC. Okay, so because I know that IC is equal to beta IB. Just to calculate IB, I'm doing all these things. So what I'm going to do, IB, I will keep it in the LHS and all the remaining things I will move to the RHS. So here what you have done, so here we have just skipped one step we have skipped. Okay, so in the examination, if people can write only this much, it's okay, fine. So if not, if you are getting it confused, you can just do the intermediate step. So what is that step we have skipped here? So IBRT plus VBE plus, so here 1 into IB, right? Okay, so what you go first one select plus beta IBR. Okay, so from all these things, what we are taking IB. Okay, so when you take IB common, okay, so all these things will be there in the bracket, and in the other side, what you have to do? So only this VBE you are sending it to the VT minus. So here, when you take IB common, what are the things that will be remaining here? So here, from this term, you plus from this RE, this term you will get beta RE. Okay. Also RE plus beta RE, what I'm taking RE common. If you take RE common, so here you will be left out of 1 plus beta. Okay. So dt minus VBA, and keeping only IB this side, all the remaining things we will send it to the denominator of the RHS. So we will send it to the RHS RT plus 1 plus RE. Okay, so can we skip all these things? Yes, you can skip. So if you feel that if you are getting it confused, so only this step you can write and you can skip these 2 steps. Okay. So you got the IB value. So now when you substitute this here in this, so you will get the IC value. Okay. So one value I got. What you are going to do? Find out VCE. What you are going to do? You will apply KVL to the output. Okay, so when you apply KVL to the output circuit, so it will start from here, VCC minus ICRC minus VCE minus IER is equal to 0, and you can see here. Okay, so and collector, so here we will consider emitter current is approximately equal to collector current. Okay, so here by considering that one, so when you so if you want to calculate VCE, what you are going to do, so in place of IE, we have to substitute IC. Keep VCE on one side and keep all the remaining things on the another side of the equal. So then you will get VCE is equal to VCC minus, if you take IC common, IC into RC plus R. Okay. So now what you are going to do, so once you are done with these things, so you please derive all these in your rough note. Okay, so before or in your notes, ADE notes, so before writing in the assignment. Okay, so all these definitions, which are those 6 definitions, so calculating IC for fixed bias, so this one, okay, so calculating VCE for this one, so you will observe all those 6 are one and the same. So just write the circuit. So guys, this is a homework for today for you. Okay, so what you're going to do, so I will upload this by the end of the day. Okay, so before coming to the tomorrow's class, this homework you do now itself. So this will help you guys. Okay, so what you do, you just write this, just by seeing only you write. No need to, anyway for internals only you will copy paste. You listen to us. Okay, fine. So by seeing only you write this diagram and you write, calculate IP and calculate, substitute it for IC and calculate VCE. Okay, so next you write collector to base bias, the circuit you write, this equations derive it for the IV value and you calculate the VCE. So similarly, you write the circuit for approximate with it, calculate IE value, IC value and calculate VCE. Similarly for Thevenin's, you do both KVL, applying KVL to input and applying KVL to output. Okay, so this you need to practice. Only by practicing you will get it. So in the examination, one for sure you will get it. Okay, so the homework is just to write it by seeing those 3 derivations. Am I clear? Okay, so this completes the
document.
If at all while solving, if you're getting any doubt, you people can come back to us, you people can ask us. We are ready to solve that. Okay. So this completes the biasing of all those 3. So guys, it is not that difficult. It's okay even if you're not understanding why it is, how it is. So just to make sure that, so if you are understanding the KVL well and good. So if you are interested, if you are having any doubts in that, we are ready to clear that also. So if not also, so what we are telling you is, so no need to worry too much on that. Okay. So guys, C section guys, now I'm seeing your messages. Am I audible now? Are you listening? B and C section, above 90. Okay. Okay. So did you listen to that homework part and all, or only that was not audible? So homework you will do, right? So just to write those 6 derivations, okay? Okay, so let's move on to the next thing. That is the comparison of various biasing techniques. So this is not at all difficult. So they have just compared all those three circuits. So whatever we have discussed, just listing it down. That's it. So coming to the circuit here, you are seeing all these three circuits. So guys, instead of taking those complex circuits, whatever here this notation you have, so if you can just remember this, you can just write this. Okay. So here it's very simple. The same thing is there. Maybe the voltage and this representation they have. It's not there. That's it. Okay. So, but while writing the derivations, you have to write VB. Okay. So and here we see is this. Why we will that in the derivation because we apply KVL, right? Right. So that VB, the same you will get confused while applying KVL. So that's why we'll derive. Okay, so here for comparison, you can just write this simple circuits. And moving on to the next parameter, stability provided. Coming to the circuit, I guess so there is no confusion. So here connected to base bias because this connector, this is establishing connection between this collector and this terminal. Okay, so this is voltage divider because we are using that circuit. So how you what generate or implement a voltage divider by a circuit? The applied voltage VCC is divided into two. Okay, so here it is divided into, here you can see the division by using these two resistors R1 and R2. This VCC is divided, one voltage you can apply it at this IB and the second voltage you can apply it here, right? So since the applied voltage is divided, this is called as voltage divider bias. So coming to the fixed bias, here a very simple circuit, just VCC is applied to same IB as well as to same this RC. Okay, so very simple circuit. So this is all about the circuit. And coming to the stability, here we know that we have already discussed this base bias provides less stability. This one medium stability, the stability provided is more compared to base bias but less compared to voltage divider bias. But now when we compare these three, this voltage divider provides the highest stability. So coming to the feedback used, here we are not using any feedback. Okay. So here we are using negative feedback. And what is this voltage shunt negative feedback? Here also we are using negative feedback. What is this voltage shunt and current series? So guys, this if you learn this feedback circuits, I don't know whether you have studied this in your previous semester or not. So basically there exists four. So if you're not understanding it, don't worry, just forget it, just neglect it. You can simply write negative feedback. You will fetch marks, okay? So no need to worry about that one. If at all, if some students who are there who knows all these things, only they will understand. Those four type feedbacks are voltage shunt, voltage series, current shunt and current series. So what are these? When I give voltage as a feedback, okay, so voltage as a negative, these are the four types of negative feedback circuits. Okay, so what I'm doing, I'm giving voltage back, feeding the voltage back to the, giving some portion of the output voltage to the input. So then it is called as voltage negative feedback. If you're giving the current, voltage output current, you're taking some portion of the output current and you're giving it back to the input, then it is called as current feedback. Okay. So here you can give it in two types. If I'm giving it in the series, if that negative feedback, I'm giving it in series to the input, then you are going to call it as current series feedback, voltage series feedback. If you are giving it in parallel, then it is called as shunt. That's it. So you can see here. So here this is in shunt, correct? So whereas here it is in series with this one. Okay, so that's why don't worry too much about all those things if you are not understanding it. So coming to the application, so here used in a circuit where stability is not an important criteria. Okay, so here it provides medium stability, so that's why you can use these collector to base bias in switching circuits. Okay, so coming to the voltage divider bias, since the stability is provided, the stability provided is very high, it prevents the transistor from going into the saturation region. So that's why you cannot use it as a switch. So what you can do, so you can use it in the devices where the stability is more. So you can use it for the voltage stabilizers in any electronic circuits, as voltage stabilizers in the electronic circuits. Okay, so this completes the biasing thing. So coming to the syllabus, So I'm just displaying the syllabus. So here we said that we are going to start it with the BJT biasing, right? So in the BJT biasing, we saw 3 types. Okay, fixed bias, collector to base bias, and voltage divider bias. Okay, so these are the three things which we have covered now. Okay, so now we are moving on to this portion. Okay, so we are seeing the photodiodes, light emitting diodes, and optocouplers. So these 3 topics we are going to finish it. So after this, let's move on to the op-amp. Okay, so guys, don't worry if you're not getting it. So just to try to understand what are the things that will be asked in the examination and what you need to write. If at all, if you are not getting even one single point also. Okay, so no need to worry. So once the subject start getting interested, once we start with the module 2. Okay, so since this module 1 is theory, we're hoping that offline classes may start next month or after 2 months, something like that. So solving problems will be easy once we do it in the offline class, rather we do it in the online class. So only because of that reason we have started with a module 1. Okay, so no need to get tensed about the subject by looking only with the module 1. If you're not understanding it, it's okay, fine, relax, cool. Just understand what are the questions that you will get in the examination and what you need to write for. Okay, so I hope at least I'm making sense in those things. Okay, so what is that? First we have discussed about the transistor biasing. So in that we have seen 3 types, and what have we seen in these 3 types? So 2 derivations for this one, IC derivation, VCE derivation. What are those 2 IC and VCE? They are the operating point. So what do you mean by operating point? The job what I'm getting done from by using this transistor is amplification. So what is amplification? Strengthening a weakened signal is nothing but an amplification. So why do you need that? When if the signal it goes on contracting or reducing, then the strength will not be there. Or if, for example, if it's an audio signal, if you don't amplify it, you will not listen. So amplification you will do so that you can listen that voice through the speakers, right? Okay, so that's why amplification of a voice signal you are going to do. The same applies everywhere. Okay, or it can be used simple repeater also. Okay, so to do the amplification, the transistor should be stable. Okay, so it should not go here and there. It's not physically moving here and there. Okay, so the operating condition shouldn't be. IC value, VCE value should not vary. Otherwise, noise get introduced into this one. So whatever the actual signal is there, I just want to amplify only the actual input signal. I don't want noise to be introduced in that one. So that's why it's very important for me to maintain proper IC and VCE. How do you get that IC and VCE is what we have seen so far. Okay, so what we did, we just saw the derivation for IC and VCE by using fixed bias, IC and VCE by using collector to base bias, IC and VCE by using collector voltage divider bias. Okay, so this is what we have discussed, and this is what they will ask. In 2 problems we have seen, and that 99.99% whatever the things that you're going to problems that you're going to get here, you will get it from the worked example itself. Okay, so it's very rare that 80% of the times you will get even the same values. Only 20% of the time they will change the values. Okay, so don't neglect numericals here. So just try to practice whatever we have solved in the class. That's more than sufficient. If you by heart this memorize this formula, if you know this formula, even if they change the numerical values, people can easily attempt and you can score marks even in the numericals also. So no need to get afraid of this subject. Okay, so moving on next, let's start with the next topic. So guys, before moving to the photodiodes, any doubts for anyone? Homework part was not audible. Okay, so let me just repeat it for you guys. So what you need to do, so these 3 circuits you should take. Okay, so I'm just uploading this file by the end of the day. So you need to write this one. So in your notes. Okay, so again you will write the same thing even in your assignment, but I want you guys to write it 2 times. That's why I'm telling you. Okay, so take your notes. So copy down this circuit, copy down this derivation, IC derivation, VCE derivation. So next move to this circuit, copy down this circuit. So derive this IC and derive this VCE. Okay. So next copy down this circuit, derive for IC, derive for VCE. Copy down this circuit, write the derivation for this thevenins. For all those 3, you just derive by seeing only. You write the derivation for all the all those three biasing circuits. So that is the homework part. Okay. So maybe probably I'll provide, I will create a link in the byword and I will ask you all 180 people, I will ask you to upload that homework. So make sure that you write it. So by writing, you will get the confidence and you will also understand that it's not that difficult. So that's why I'm giving this homework. Okay. So write so that you will understand what is the relationship between that IC and PCE. Okay. So you will understand it's not that difficult even if you have not understood it. Okay. So any doubts before we move on to the next topic? So guys, I'm expecting reply. No doubts. Okay. So then let's move to the next topic. Photodiode. So what exactly this photodiode is? So it's also a type of diode. So then what is the difference between a normal diode and this photodiode? So in the normal diode, so we are going to apply that voltage and we will get the same voltage or current as a output. Okay. So whereas here in this diode, what happens? Input applied is the light. Okay. So the output will be the electric current or voltage. So what can you call this photodiode as? So you can call this photodiode as a device, semiconductor device, which converts light energy into electric current or voltage. So which converts light energy into electric energy. Okay. So that output could be in terms of current or voltage. Okay. So once you say that it converts light energy, so it means that you can call it as a light detector. Correct. So it detects the light. It should be capable of detecting the light. Then only it can take that light as an input and it can convert it into the output current or voltage. Right. So this is what you can write for photodiode. And now whatever that normal PN diode we had, so why can't we use the same thing? And why, what is the use of this light here? So that comes the question. Okay, so in normal diode, what happens if you want to, even this you might have observed even in the zero diode or whatever it is. So when you apply a reverse bias to a normal PN junction, so normally you will get a small amount of current. Correct. So the current, whatever you're going to get in the device in a normal PN junction, when you connect it in the reverse bias, is because of the minority carriers what we have, right? Okay, so that minority, what is the population of the minority carriers? Obviously, it's very less. Correct. So because the carriers are less, whatever the current we are going to get is less. So that makes sense, right? So now if you want to increase the population of the minority carriers, what is that possibility we have? We're going to increase the reverse bias voltage. Okay, so when you increase the reverse bias voltage, yes, to some extent the minority carrier population will be increased. But before they cross the junction and before they convert, before they turn into current, what happens? The newly generated carriers, so they recombine with the same material majority charge carriers before they cross the junction. So once that recombination happens, so again you don't have free holes or free electrons to produce that current. So thereby there is no possibility of increasing too much of current in the device. So are you getting this one? So that's why what happens, so that crossing the junction itself is problem. So there will be more majority carriers waiting. As soon as they see the minority carrier moving, so they absorb that one and the recombination takes place. So by which the current won't increase. So they should cross the junction, and this story you people know very well, right? So these free electrons or free holes, they should cross the junction so that they can contribute to the current, correct? So they contribute to the flow of the current in the device. Okay, so to pass the junction, it's difficult here. Okay, for the minority charge carriers in the normal PN junction. So that's why we have very small amount of current in the reverse bias condition. So if you keep on increasing this reverse bias voltage, what happens? So after this one, so the junction breaks. So once the junction breaks, so there will be a enormous amount of increase in the current, correct? So, but that is not useful for us. And the same thing we have also observed seen in the Zener diode also. So now what we are going to do, so to overcome this problem, we cannot increase after some threshold. So to overcome this problem, what we are doing, we are directly applying the energy to the depletion region. Okay, so how can you do it? You cannot connect any battery, something like that, to the depletion region, right? So because you need a cathode or anode terminals to take out. So which is not possible in a normal case. So what you're going to do, instead of the electricity, you're going to apply light. You can easily apply light there to the depletion region. So this light energy acts as an input and it helps in generating more charge carriers. Okay, more minority carriers. So since they have since the input is given at the depletion region itself, so the new charge carriers formed easily cross the junction. Yes, here also some recombination will take place, but the number of charge carriers that cross the junction are more when compared to the normal PN junction. And since more number of charge carriers cross the junction, the current produced is also more when compared to the normal diode. So this is the reason why we are going for this photodiode. Why are we involving light in our diode? Okay. So next we'll move on to the I don't know whether this scanned image is visible or not. Let me just explain. Okay. So here you can't differentiate. It's completely looking as a black box. So let me just explain it. So what do you have in the construction? See, in this construction, what you have to do, so you need to form a diode, right? So you have to form a diode in the sense you have to form a PN junction. So how PN junction is formed? So P type and N type is brought together so that the diffusion layer is formed. Correct. So here also the same thing we are doing, but here whatever the technique that we are using, it is called as ion implantation. Okay, so here the PN junction is formed based on the technique called as ion implantation. And what is this? Nothing. Whatever we are doing it, the same thing here also we are going to do. Okay, so but we are giving that name as a ion implantation. That's it. Okay, so what happens here? So here you're going to take a N type semiconductor. Okay, so you can see this is N type semiconductor. Okay, so here what we are going to do, a P-type material we are going to take. So this P-type material will be bombarded here. It will be diffused, or almost it's like a diffusion entry. Okay, so this P-type material will be bombarded here so that it produces a P-type layer about after some distance here, so that here the depletion region occurs. So what happens while forming this depletion region? So because here N layer was there, you brought P layer above this N layer. So obviously what happens? The flow of charge takes place. The excess electrons from N layer will go to this P layer, and before what achieving the equilibrium, the excess holes from the P layer, they will come here, they will travel to the holes from the P layer, they will travel to the N layer. Okay, so and after this, all these traveling happens, it achieves equilibrium at some point, and this depletion layer is formed. Okay, so you know the depletion region. So here all this here positive ions, and here between all the negative ions will be formed, forming the depletion region. Okay, so now what happens after this, after the formation of this depletion region? So they are going to coat this SiO2. So what is this SiO2? SiO2 is a dielectric, it's an insulator, right? So this dielectric SiO2 is coated above this one. Okay, so but here what we are doing, we are not completely coating. So this entire rectangle portion is not coated with SiO2. So we are just leaving a space. So if this is a surface of this diode, so here we are leaving some window, and all these will be coated with SiO2. Okay, so only this window is not coated with SiO2. So why? So because we have to pass the light energy here, right? Okay, so we have to give the light energy. This is where the depletion region is there, and here we have to pass the light energy. Okay, so and here whatever this window is there, so here we have coated this anti-reflective layer. So what is this anti-reflective layer? We are making use of silicon nitride, SiN. Okay, so we are coating this portion with anti-reflective layer. What is the use of coating this portion with anti-reflection reflecting material? So that whatever the is, because the input we are giving, you know the tendency of the light. Once you what? Yeah. So once you one, give a light, or when you put a light on some surface, that's depending on the surface thing, you have this reflection thing, right? So but here we want this energy to be absorbed properly, because we have to convert this into electrical energy, and we can't let this light go waste just by reflecting. We don't want any light ray, any photon ray to get reflected. So that's why we have coated this with the anti-reflection. Okay, so whatever the light that you're going to incident on the surface, so everything should be absorbed here. Okay, so everything should be absorbed, and it should used to convert. It should be used in convert or producing the current in the device. Okay, so that's why it is coated with this anti-reflective layer. Okay, so after this construction, so we need about, we want cathode and anode, correct? So here I coat an aluminum. Okay, so aluminum coating is done here on the top of this one, and this is fetched to make an anode terminal. Okay, so similarly at the portion here, what I'm going to do, N plus region I'm going to form. So what is this N plus region? I'm going to just heavily dope this region. Okay, so a heavily doped region is called as plus. If I heavily dope a N type material, then it is called as N plus region. If I heavily dope a P type material, then it is called as P type region. Okay, so here I am going to fetch a cathode terminal. So here you have a anode terminal, here you have a cathode terminal. So guys, did I scare you by telling this construction? So nothing much. Fine, even if you have not understood, no need to worry. Just forget this one. So what are the things you need to write? You will have a N layer upon which you will take a P layer and bombard it. And this method is called as ion implantation. Only this word you need to memorize, and this you have to write and you have to underline it if you want full marks. Okay. Construction is done by using ion implantation. What is it? Just take the N-type material and bombard it with P ions on the surface of it. This one. Okay, so depletion region forms just by attaining equilibrium. Excess electrons from N-type flow to P-type. Excess holes from P-type travel to N-type. Depletion region is formed. Once you say the depletion region is formed, diode is formed. Correct? Okay. So next you will write about the silicon. Third point, you will write about the silicon dioxide. Silicon dioxide is coated here, insulator. Yes, it is required. So only some portion is allowed left free for the light to incident, and to that portion you're going to coat it with the anti-reflective. And next, how anode is formed? By an aluminium coating. By aluminium rod, you will make an anode, and with a heavily doped N plus region, you're going to form the cathode. Only 5 points. That's it. Even if you have not understood why all those things, it's okay. So 5 points you write. You will get the marks of the construction. Okay. So once you're done with the construction, so we have to move to the working principle. How exactly this photodiode works. So before that, let's see the circuit diagram as well as the symbol. So this symbol is very important if they ask this question in the even though examination. Okay. So even though if they have not given it explicitly to write the symbol, it's your duty to write here the symbol. Okay. So otherwise, definitely you're going to lose some portion of the marks. Okay, so 1 marks they're going to deduct it if you don't write the symbol. Okay, so what is this or how to represent this photodiode? So the symbol is very similar to your normal diode. So what is the extra fitting that you are seeing here? only this light is, correct? So in the normal PN diode, what you're going to do, you're going to connect it, give electric current or voltage as the input, correct? But here we are giving light as the input, so which is denoted by using these two apps. That's it. Okay, so that is what the extra fitting what you need to do or do to a normal PN junction symbol. That's it. Okay, diode symbol. Okay, so the same thing if you want to show it in the circuit, here in the left hand side you are seeing the circuit. So what do you have here? Here you have a diode, P type, N type. Okay, and I have already repeated several times, this diode works in the reverse biased condition. So that's why P type you have to connect it to the negative terminal of the battery, and N type you have to connect it to the positive terminal of the battery. So you just connect one resistor here, and here light. This is the extra fitting when compared to the normal light. Okay, so that's all. Very simple, correct? So very simple connection. So this is what the circuit of a photodiode, and this is the symbol of a photodiode. Okay, so now how exactly this photodiode works? The same story here, I have to repeat it now. Yeah. Okay, so this is how it looks. So well, these two diagrams are not there in your textbook. Okay, so this I have taken it from the net so that it will be easy for you to understand it. Okay, so whatever the explanation it is there here, I'm just explaining it by taking these two. So once the diode is formed, this is in the reverse bias condition. You can take these two. Okay. So this, while cutting, this has gone like these things. So this should be a battery terminal, negative, and this one positive. Okay, so you change that. So here, this is how it will be there before applying the light. Okay, so once the equilibrium has achieved and the diode is formed, after you bombard a p-type material on the n-type material, so this is how it looks. Correct. So depletion layer is formed, and here you have all the negative ions, and here you have all the positive ions, and this is what you're going to call it as a depletion region, right? Okay, when you connect a negative terminal of the battery to p-type and positive terminal of the battery to n-type, we know in the reverse bias condition the depletion region expands, widens, right? Okay, so now you want the flow of current. So now whatever the current that is there flowing in the circuit is very less. Okay, so now you want to increase this one, correct? So for that, what you're going to do, you're going to incident the light energy here to this junction. Okay, so this is how you're going to do. So when you incident a light energy to this depletion region, what happens there? The photons present in this light energy, so that will help in the production of new charge carriers. So what is the meaning of it? More number of free electrons and more number of holes will be formed. How, ma'am? How more number of electrons and how more number of holes will be formed? See, because of the recombination, you have these charges accumulated here, correct? So what do you mean by a negative ion? So negative ion means, so here one electron is more, the number of electrons are more compared to the, that is what an ion is, right? So the number of protons and the electrons are not equal in number. Either you will have the ion is formed just by gaining one extra electron or by losing an extra electron, correct? So if it loses an electron, then you're going to call it as a positive ion. If it gains extra electron, then you are going to call it as a negative ion. Okay, so once from the photon, it takes this positive and the recombination takes place and it becomes a charge carrier. Got it? So here also from this photon, it will take a negative ion, one extra electron it will take because it has lose the electron. Positive ion has lose the electron. From the photon, it will take an electron and this becomes a charge carrier. Recombination happens and this becomes the new charge carrier, correct? So this is what the story is. So and you can see here. So once this light is incident here, more number of charge carriers. So you can see the ions have reduced here. And do we need to write all this story? No, sir. So if you have interest, if you have understood it, yes, you people can write by taking these two. So otherwise, no. So you can just memorize these things, whatever I'm telling it, the same thing it is there. So because of the incident of the light, the photons help in producing new electron hole pair. So where the new electron hole pair will be formed in three places it will be formed. New electron hole pair will be formed in the depletion region, it will be formed in the P region, and it will be formed in the N region. Okay, so new electron hole pair will be formed in all these three places. Along with this, some recombination will take place. Yes, but let's neglect that one. But that point you have to write. But since the number of the free electrons and holes have increased, so they will start on this. Okay, so here it widens, and you can see here the free electrons will start. Okay, so the free holes will start in this direction, and free electrons will get attracted by the positive terminals of the battery, and they will start moving this side, which results in the flow of current in the device. Okay, so that is what explained here. Okay, that's how this light energy is converted into electrical energy. How it will be converted into energy? With the help of photons. That's it. So this is how the diode works. So any doubts? You understood? So let me just check the chat. Any doubts? You want me to use black color? Okay, sir. Okay, Mansh. From next time I will use black color. So yeah, I was using this red color because black I get confused. Okay, fine. I will take up the black color. Okay. So any other doubts? You understood? Oh, you're getting it, then I'm happy. You're getting it. Okay, let's move on to the VI characteristics of a photodiode. Okay.
Separate ಅಂದ್ರೆ ಚೈನಿಗೆ ಇದು ಆರ್ಡರ್ ಇದೆ ನನ್ನ ಆರ್ಡರ್ ಇದು ಜಾಕೆಟ್
So coming to the VI characteristics, what is this VI characteristics? So this is not the first time that you are seeing some VI characteristic curve, right? So what exactly it is? So you're going to this is a graph. VI characteristics is nothing but a graph which shows the relationship between input and output. So in particular, it shows the relationship between the voltage and current. Okay, so input voltage and output current. Correct. So this is what a VI graph is. So what it gives us the relationship between the input voltage applied with that of the output current generated. So this is what a VI characteristic curve is. Okay, so here you can see this is the reverse bias voltage that you have applied as the input, and this is the forward bias voltage that we have applied as the input. Okay, and this is the current that has produced. Okay, so here you have a V and here you have a I. That's why this is called as VI curve. Along with this V, we have one more input here. What is that? Light is what we are giving. Correct. So light energy is we are giving it as a input. Okay. So if I'm not giving any light, means dark current. Correct. So which shows this one, this condition here. Okay. So here I have just connected the terminal. I have just connected the diode to the terminals of the battery. That's it. Okay. So here we have not given any light. Okay. So we are not given any light. Only that we have connected it to the battery. Okay, so this first curve is telling about that. You can just see. So the flow of the current is very less. So if this is minus 100, let's take it as minus 50. Okay, so like this. It's very less, small amount of current, and this is what happens even in your normal P. This is nothing but your normal PN diode, correct? So even if you use normal PN diode, so it will be like this, very less. But when I incident a light of 10,000 lumens per meter square. So here the amount of current that is flowing, it increases up. Yes, in the negative side, because we know that the diode itself is working in the reverse bias. Okay, so that's why we are getting this VI curve also in the negative region. Okay, so next minus minus region. So next, if I increase the intensity of light, if I increase the intensity of light to 15,000 lumens per meter square, the current also increases in the negative side. Okay, so if you increase it, again you are going to get it, and you can see here the saturation attained. Whatever the curve that you are seeing here, the upper going curve, that is a saturation region attained. Okay, so you can see here the saturation attained will also, the time taken to increase the saturation is also increases, correct? So it goes like this, and it is going here linearly, where this saturation is going to achieve this point. We are going to call it as, we need it next. Okay, so we'll see. Okay, so this point where the saturation is attained, this point we are calling it as. Okay, so this is what the VI characteristic curve. So here the current that is flowing in the device is given by this formula. Okay, so what is the formula? I is equal to the formula you need to write. Okay, so guys, and what are the things they will ask? So they may ask you, the possible questions on this topic is, so explain about photodiode. Okay, so if that is a general question, right? So in this photodiode, what are the different topics that we have? One thing is we have construction. Second thing is we have working principle. Third thing is we have, one second, ma'am. Heli ma'am, you know? Huh? Yeah, so I was explaining you regarding the question, right? So they may ask you, yeah, what are the things that we have in this photodiode? We have construction, we have working principle, we have VI characteristics. Okay, you also have application. So these four topics out of these, what are the things that you have to write? So if they ask in general, my suggestion would be to shortcut everything depending on the marks. So if they have asked for 10 marks, then you can't shortcut anything, right? So everything you will write it. Okay, so all those diagrams you will write it, and explanation, 3 to 4 lines you will write, and you will end it for 10 marks if they ask. And they won't ask more than 10 marks these questions. Because if it is as 12 marks, then you people are very lucky. As it is, you will reproduce. That's it. Okay. So then a bit with more explanation. That's it. So if they have not asked for 10 marks, so you can just, if they have asked for 8 marks. So the main thing what you have to concentrate is concentrate on the diagrams. Okay. So if they have asked for 8 marks, you can write, these two are extra diagrams which I have given. You can skip these things. Okay. So these two not required. You can skip only these things you can write if they have asked for 8 marks, and all this construction only in 2 lines you can write. It consists of this. Working principle, you just explain it, and this you write. Important, this one. Okay, so this you write, and this explanation also you can shortcut. Okay, so this is what you people can write if they have asked for 8 marks. If they have asked for 4 and 5 marks, so then the same thing. You can concentrate more on working principle. And with these two diagrams, you can just write 1 and 2 lines of explanation. Okay, so more concentration on the working. So sometimes what they will do is they will separately ask. So explain the construction of the photodiode. Then it will be only within 5 marks they will ask. So it could be for 3 marks or 5 marks, 4 marks, something like that. Okay. So then you will have to write only this way. Maybe one symbol along with symbol and one sentence explanation of working would work. Okay. Or application, something like that. Okay. Or simply they may ask working. Okay. If they have asking working, then one line explanation of construction and one sentence of application you can do. Okay. So VI characteristic alone they won't ask. Okay. So normally they won't ask. So if they ask also, it's not that very difficult. In that, what you can do, there also you can write more explanation of working, and you can write few things in this VI characteristic. Okay, so application, make sure that you write. So instead of depending if it is asked for the less marks, so instead of writing these 3 points, we can see the applications here. So what are these three applications? They are used in consumer electronic devices like smoke detectors, compact displays, televisions, remote controllers, in VCRs, clock radios, camera light, street light. So it's used in the places where exact measurement of light intensity is required. Okay, so all these 3 points, you people can club it as 1 point, right? So depending on the marks, you present your answer. So when if it is asked for less marks, so you can just remember 3 or 4. It is used in the devices like smoke detectors, camera light meters, street lights, something like that. Okay, and you people are very good in doing all those things. Okay, but some people has to improve. Okay, so the amount of knowledge what you people have, it's one and the same. So which lies in that average this thing, right? So those who are scoring, I don't know in your this thing, let me tell you in the marks. So those who are scoring above 60 to 80, all of you will have the same knowledge. But what it varies is your presentation matters. Okay, some people will read neatly, right, present it properly by considering all these points. That's why they will score more marks. That's it. Okay, so you need to improve only a bit in your presentation skills. That's it. So with this, let's move on to the attendance. So guys, let's just take 2 minutes break and let's complete the attendance. Today's date is 7.
Like class, just type your USL, type and click.
Okay, guys.
As soon as I call,
So
just you
everyone, please type your USN and then
enter.
so as soon as I call.
USN 1. USN 1. Asta. 2.
Navyashri,
3. Asta present. Okay, USN 3. 4. 5.
Navyashri,
6.
hello.
7. 8. USN 8.
So wait. Navya,
Okay, then 8 is absent.
Naina.
Yeah. 9.
So guys, you can you
10.
type your USN and be ready. As soon as I
11.
call name, you can just enter that your USN.
11.
So don't
12.
type present. I'll get confused. Okay, Nayana. Okay, fine. Nilisha.
13. 14.
Okay, Nilisha is absent.
15.
Niharika.
16.
Niharika is absent.
17.
Niharika, are you there? Yeah.
18.
Niket. Nikhil. Nitish.
18.
So guys, make it
Ankit?
fast. Nitish is absent. Okay.
Hey,
Omkar.
let me call. Who is that Omkar? Can't you wait?
Omkar allogin agidana. Tell
98
him that I have
present.
given attendance.
18.
Avinash.
Ankit.
Avinash.
19.
Absent.
20.
Sai Tarun.
21.
Avinash.
20. 21 is absent. Anusha.
Sai Tarun.
21 present. 22.
Padmini. Now,
23.
sorry. Now
20
Tej.
is present. Hey, please guys, after I call you,
Yeah.
press enter. 21
Sudarshan.
present, 22 present, 23 present, 24 present, plus 25,
Sudarshan.
25. Babushya, I think absent. 26,
Pavan. is not
26, 27,
there. Pavan, are you there? No. Yeah, Pavan Kumar.
27. Shri Ash, I think is absent.
Okay, Pavan given.
28.
Nishant.
29,
Nishant. Kaushita.
30,
Kaushita present.
30, Chandan,
Pradeep, yes.
31,
Pradeep.
31, 32,
is not there. Prajakta. Prajakta
32
is there.
Chaitanya.
Prajwal R.
33, 34,
Prajwal, why Prajwal is not attending?
35.
Prakriti. Yeah.
35,
Pranav.
Chitra,
Prarthana.
36,
Prarthana P. Prashant.
37,
Prati.
38, 39,
Praveen. Yeah, I saw your name.